Alright, so we're starting to talk about chemical reactions, and we want to learn how to do two things. So one, be able to predict the products of different types of reactions, and also to balance the equations for those reactions. First, we need to talk about what happens when we put different types of compounds in water. We have three different scenarios. So one is we have a strong electrolyte, and these are going to be compounds that completely dissociate in water. And this means that they split apart into ions. For example, if we have sodium chloride table salt and we put it into water, we get Na plus ions and Cl minus ions floating around in water. There are two other types of strong electrolytes that we should look out for. One is a strong acid. So anytime we have H plus paired with some anion, it could also be a polyatomic ion, it's also going to completely dissociate in water. And what we would get is H plus ions floating around and Cl minus ions floating around in water. The last one is going to be a base. So we said hydrochloric acid. Anytime we have a metal paired with hydroxide, OH minus as our anion, these are going to be bases. And this is a strong base, so it also dissociates completely, splits apart into ions in water. What we get is Na plus and OH minus when we put it into water. Remember that polyatomic ions stay together, so those atoms will stay together. What happens if we have a weak electrolyte? So these are going to be compounds that only partially dissociate in water. One example is acetic acid. This is what gives vinegar that acidic taste. When we put this in water, we get H plus and acetate. We get both of those ions, but some of it stays intact. We also just have acetic acid that doesn't break apart into ions, so only partially breaks apart into ions. Okay. Now we can start to talk about equations. One that I think we've seen a few times, but we haven't given it a name, is a precipitation reaction. So this is going to be, one example is a double displacement reaction, and we're looking for forming a solid product. For example, if we have lead nitrate in aqueous solution, so that means it's dissolved in water, and we mix that with sodium sulfate, also in aqueous solution, the first thing we're going to do is swap partners. So the cation, the lead, from this compound will now pair with the anion, the sulfate of the other compound, and the sodium will now pair with nitrate. So we can write both of those products down. Again, this is a precipitation reaction, but you can also call it a double displacement reaction since we switch partners. We get lead sulfate and sodium nitrate. The next thing we need to figure out is whether or not these two compounds dissolve in water. So if you look at your solubility table, you'll see that lead sulfate is insoluble in water. So we write solid next to it, whereas sodium nitrate is soluble in water, so we write aqueous next to it. So once we've predicted our products, and we know whether or not they dissolve in water, the next thing we need to do is balance our equation. So the number of atoms of a specific type that we have on the left side, that's called the reactant side, we have to have the same number of those atoms or polyatomic ions on the product side or on the right side. It's best to start with the metals first, and then let's see how many we have on each side. So we have one lead atom on the left side, the reactant side, and we have one on the product side. We're good there. We have two sodiums on the reactant side, but we only have one on the product side. So we need to start adding in coefficients to balance this out. So on the product side, we want to add a coefficient 2 here. So now we have 2 sodiums and 2 nitrates. Remember that the coefficient counts for both. And now we're balanced. Let's go back and check one more time. We have 1 lead on each side, 2 sodiums on each side. We can treat the sulfate as a unit, so we have 1 sulfate on each side, and we have 2 nitrates on each side. So our equation is now balanced. The next thing we want to write is something called a complete ionic equation. And this is where everything that has aqueous next to it, we're going to break apart into ions. Because remember, these are strong electrolytes. They split apart into ions in water. Let's start with the reactant side. So we have lead, 2 plus. Remember, we need to write the charge since it's splitting apart into an ion, and we also have to write aqueous next to it. We have 2 nitrates. We have 2 sodium ions, and we have 1 sulfate ion. I'm running out of room, so I'm going to put our arrow here going to the products. Remember that lead sulfate is solid, so that doesn't break apart into ions in water. We can just write it how it is as lead sulfate. We still need to write solid, but the sodium nitrate we need to break apart into ions. Remember that our 2 out in front, our coefficient tells us we have 2 Na plus aqueous and 2 nitrate, NO3 minus aqueous. What we do next is we want to see what ions we have both on the reactant side and on the product side. Because if it's not changing in the reaction, then it's not actually doing anything in the reaction. We can get rid of those. We have 2 nitrate ions on both sides, so we can cross those out. We also have 2 sodium plus ions on each side, so we can cross those out. Now we're left with only the ions that are actually undergoing the reaction. That leads us to our net ionic equation, where we bring everything else down that we didn't cross out. So we have lead 2 plus aqueous ions coming together with sulfate ions to give us lead sulfate as a solid. So this tells us only what's reacting. Let's look at some other examples. So for all precipitation reactions, these are going to be non-redox reactions, meaning that electrons aren't being shuttled around in our reaction. We're not transferring any electrons. But let's look at some reactions where we are moving electrons around. And the first thing we need to talk about is what an oxidation state is. So this tells us for that element in that substance, what is the charge that it has? And we have a few rules. So any substance in its elemental form is going to have an oxidation state of 0. So not just our atomic elements, but also our molecular elements. So all of our diatomic elements will still have an oxidation state of 0. The oxidation state of an element in a compound is going to be the same as its charge. So the same way you use charges to figure out formulas, you can figure out the charge in that way. And then the last thing we want to do is figure out, is it a redox reaction? So another name for this is an oxidation reduction reaction. And we have to look at if the elements on the reactant side have the same charge as they do on the product side. So if the charge changes, that means electrons are being moved around, and it is a redox reaction. If the oxidation state on the reactant side and product side are the same, then it's a non-redox reaction. Let's practice determining what the oxidation state is for different substances. For example, we have H2 hydrogen gas, and since it is a molecular element, it's in its elemental form, it has an oxidation state of 0. The same for iron. If we just have iron solid, iron metal, it has an oxidation state of 0. What about iron sulfide? In this case, we have a compound, so we need to figure out what the charge is for each of the elements in the compound. Sulfide always has a -2 charge. So to balance that out, we have one iron that has to have a +2 charge. So that tells us what the oxidation states are. We have +2 for iron and -2 for sulfur. Now let's look at a reaction. So one type of reaction where we are moving around electrons is a type of gas-forming reaction. So if we take sodium metal and we add water to it, this is an extremely exothermic reaction. This can actually catch fire. We're going to produce two products. We have sodium hydroxide, which we said is a base, and it's a gas-forming reaction, so we're making hydrogen gas. So this is one of the reactions you have to memorize. Anytime you take a metal, so an alkali metal, and you mix it with water, you're going to be forming base and hydrogen gas. So put a star next to this reaction. The next thing we have to do is balance everything. So on our reactant side, we have 1 sodium. Product side, we have 1. For hydrogen, we have 2. On the product side, we have 2, so we're good so far. We actually have 3, so we're not balanced. We have 1 oxygen on the reactant side, and we have 1 on the product side. So what we need to do is add a 2 here, and we also need to add a 2 here. Because when we added that first coefficient, now we have 4 hydrogens on the product side, so we added a 2 in front of the water to balance that out. Let's go through one more time and make sure everything is balanced. So we have 1 sodium on the reactant side. We have 2 now on the product side, so we need to actually add a 2 here as well. We have 4 hydrogens on the reactant side, and we have 4 on the product side. We have 2 oxygens on the reactant side and 2 on the product side. So we are good, we are balanced. The next thing we need to do is write our complete ionic equation. So remember that sodium is a solid, so we leave it as is. And water is a liquid. We're also going to leave that as is. Remember that the only thing we're splitting apart is something that has aqueous next to it. So the sodium hydroxide we can split apart into ions. We have 2 Na+, and we have 2 OH- aqueous. Hydrogen gas is not aqueous, so we're going to leave that as H2, exactly how it is. Now let's look at the reactant side and the product side. Is there anything we can cross out? No, we don't have any ions even on the reactant side. So our net ionic equation is actually going to be the same as the complete ionic equation in this case. Now we need to figure out whether or not it's a redox reaction. Let's look at the oxidation states for each. Let's start with sodium. Sodium is in its elemental form, so the oxidation state is 0. For water, oxygen always has a -2- charge, and hydrogen, to balance it out, we have a +1 charge for each of those hydrogens. Now let's look at the product side. Sodium now has a +1 charge, and we have hydrogen here. It's in its elemental form, so it now has a 0 oxidation state. We have hydrogen here is +1, but we're only looking at this H2 gas. Now we need to figure out if things are actually changing. Sodium here is going from the oxidation state of 0 to +1. And hydrogen is going from a +1 to a 0. So yes, it is a redox reaction because the oxidation states are actually changing. Now we need to figure out which one is losing electrons, which one is gaining electrons. So sodium is going from 0 to +1. It's becoming more positive, so it's losing electrons. So this is going to be oxidation. Let's look at hydrogen. It's going from +1 to 0. It's becoming more negative, so we're gaining electrons. And this is reduction. And one way to remember this is Leo the lion says grr. Losing electrons, oxidation. Gaining electrons, reduction. So this is a redox reaction. Let's look at one more type of reaction, an acid-base reaction. And our products, based on our reactants, we're going to react nitric acid, HNO3, with potassium hydroxide. So both of these are going to be aqueous solutions. An acid-base reaction is also like a double displacement reaction. We're going to take our cation and pair it with our OH minus, our hydroxide anion. We're going to take the potassium and pair it with the nitrate. So it's also a double displacement reaction. Let's figure out what products we're forming. So the first product we're forming is potassium nitrate. If we look at our solubility table, we see that this is soluble, so we write it as aqueous. The next thing we're forming is water. So H2O, it's always going to be written as liquid. The next thing we need to figure out is, are we balanced? Do we have the same number of each type of atom, or each type of element on each side? We have 1 potassium on each side. We have 1 nitrogen. We have 4 oxygens on each side. And we have 2 hydrogens, so our equation is already balanced. Let's write our complete ionic equation. So these are both aqueous. We need to break them apart into ions. We have H plus aqueous plus NO3 minus aqueous plus potassium ion and hydroxide ion. And our products that we're forming are, this is aqueous, so we need to split this up. We have potassium ion and nitrate ion. Let's see if we can cross anything out. We have nitrate on both sides. We also have potassium on both sides. These ions that are not actually doing anything in the reaction are called spectator ions because they're not actually undergoing a reaction. Let's bring down everything that we have left. We have H plus OH minus aqueous going to H2O liquid. Another thing we can do is figure out the oxidation state, so we can figure out if this is a redox reaction or not. So hydrogen has a +1 charge, so same as the charge, that's what its oxidation state is. Overall, OH minus has a -1 charge. Oxygen has a -2 charge, and this hydrogen has a +1. That's what gives it the overall -1 charge. Let's also look on the product side. Oxygen has a -2 oxidation state, hydrogen +1 each to balance it out. So since our oxidation states are not changing for hydrogen or oxygen, this is a non-redox reaction.